Hello, my name is Innokentiy Semushin. I am a teaching professor at Ulyanovsk State University in Russia. I'm here today to talk about targeting data processing system developers to essentially increase in system operation quality. It stems from the approach I developed, as it could form a successful alternative to the Young minimum prediction error. At the data science's core is the fitting of a preselected model, for example, a linear dynamic model, to experimental data with one of performance indices, for example, the least squares criterion. However, when the model is to operate as a filter, its original performance index, OPI, remains totally inactive, in other words, non-operational. This is because the filtering error is a priori fundamentally unavailable. Our research looks into the following. How can one switch the OPI into the active mode on the filter optimization level for the adaptive stochastic data processing? The outline of our presentation includes 9 points. They can also be seen on the top bar of each slide. To begin our discussion, here are some interesting statements about models. A model resembles the original just as well a map mimics the globe. Leon Brillion. Models should not be true, but it is important that they are replicable, and whether they are replicable for any given purpose must of course be investigated. This also means that a model is never accepted finally, only on trial. George Rush. Truth is much too complicated to allow anything but approximations. John von Neumann. And finally, all models are wrong, but some are useful. Box. But what about the motivation? Consider the well-known Kolmogorov-Wiener multi-channel filtering problem. Let the correlation function of the signal be the single exponent, and all the channel noises be independent white noises. The original filtering criterion is the mean square error. If the number of channels is 2, the minimum of this criterion is J minimum, and it is given by two optimal transfer functions. In case of a single channel, the solution is even more transparent and easy to use. But what is the main point here? All the formulas for the optimal solution are available. However, the solution cannot be realized when the parameters of the problem are unknown. A filter adaptation is needed. But filter adaptation by minimizing the original criterion is not possible, as the filtering error is not available. Let us look at this case in a little more detail. We have the filter input equation and the signal generation equation. The latter is the recurrence equation of its shaping filter. Let us substitute it into the input equation, multiply by d to the power minus 1 and subtract the delayed output. We get the epsilon value, which has two terms. The first term in epsilon is the filtering error, delayed by 1 unit of discrete time. The second doesn't depend on filter parameters. It is not correlated with the first term. Squaring and averaging, we obtain our key relation, API equals OPI plus const. Available API is the mean squared epsilon. Not available OPI is the mean squared error. Both have one and the same minimizer. It is the optimal filter parameter. We try to get such result for the general case of a linear discrete time stochastic model known as the Kalman model, equation 1. An L component vector theta parameterizes the model. When all parameters theta are known, the optimal Kalman filter may be built. When not, we have to move to the adaptive Kalman filter, which is Kalman-like in structure. The original criterion is minimums of each of the quadratic indices 2 of prediction and filtering errors. They are inherent to the predicted and filtered estimates for states xt plus 1 and xt correspondingly. Remind that both errors 3 are unavailable. As mentioned, it is because of the inaccessibility of these errors that the Lyon's method dominates in the theory and practice. Note that it would be meaningless to minimize the difference between the input and output of the filter by this method. From here, we ask the main questions. Can we construct a novel filter adaptation algorithm to identify unknown parameter true theta by converging the estimated theta to the true theta without a bias? Can we offer a novel algorithm for detecting the moment of a sudden change in parameter true theta? And can both algorithms be built on a criterion-based tool, call it API, that would be equivalent to the non-operational OPI? The third question is the key one for our research. To demonstrate our solution, we executed in detail for the practical task of processing data from the field of navigation. Since we want to do all calculations manually, we limit the dimension of the data system to 4. Accordingly, the platform IN's instrumental error model in our example contains the following quantities: delta Vx, error in pins indicated velocity; beta, platform misalignment error angle; MAX, random accelerometer bias along axis X of the platform; and NGY, constant gyro drift rate along axis Y of the platform. In terms of these variables, the state and measurement equations become the physical structured data model with the given dimensions and the observability index S equal 3. Offering our solution, we highlight the following 7 steps. Introduce a predetermined set D of data sources D of theta, step 1. Identify D of true theta in D to be identified, step 2. Change from D of theta to D star of theta, the standard observable data model, step 3. Define the target model, standard observable innovation form of the optimal Kalman filter, step 4. Introduce the hypothetical set M star of CCMs, concurrent candidate models. Each candidate is obtained when the model parameter takes the jth value at the jth repetition of some iterative procedure in search of the optimal value true theta. Step 5. Consider a candidate model as the principal part of adaptive Kalman filter and supplement it with the k step ahead predictors. Step 6. And constitute a generalized residual to indicate the closeness of agreement among the actual and predicted measurements over the time instance, the number of which equals to the system observability index. A key theorem: let the generalized residual be calculated as GR formula 5 and the estimating state mismatch, which doesn't have a computer manipulable representation, be given by 6. Remark: both 5 and 6 indicate the closeness of the adaptive filter fit to the optimal filter, with adaptive filter given by M star estimated theta and optimal filter by M star true theta for a physical structured data model after transition to the standard observable data model. On the principle that the original performance index is fundamentally inaccessible, introduce the auxiliary performance index, API. Then minimum of API implies minimum of OPI, and so coincidence of the estimated theta with the true theta, and vice versa. The established practice suggests using the average value API average. For numerical minimization of API average, we suggest a gradient method in the iterative form. Estimated theta j means a selection of the jth candidate member of concurrent candidate models as defined above in step 5. Important: iterations may run over one and the same batch of measurements in a fast time scale. Using the API for monitoring system closeness to optimality. To equip the adaptive filter with an ability to perform this task, one can estimate the norm of gradient of the API and check whether this value is in a vicinity of 0 or not. Although this feature is only a necessary, not sufficient condition for the optimality of the filter, engineers can use this principle to start and stop the parameter identification procedure as it works in the vast majority of cases. In conclusion, we present a triple-tuple configuration for adaptive stochastic control. In this configuration, we have data source, system feedback, and adapter, the lower part of the chart. This configuration performs three tasks. Task 1A. It is the recognition of an event that emerges abruptly in the form of a data source parameter change to some unknown true theta value. Task 2 and Task 1B are started in parallel if this event is detected. Task 2. It is the recognizer launched estimation of the unknown parameter value by iteratively calculating an estimated theta value. Task 1B. It is the recognition of the event when we think the iterative process has resulted in a theta star which is close enough to the true theta and discontinuing this adaptive estimation process. Task 3 is started. Task 3. It is the consequent acquisition by the control system feedback of the finally estimated value theta star. Task 1A starts again. Dear colleagues, that's all I have to say. Thank you. Any questions or comments? As I said, this content is available on request from any of you to my email kentsem@gmail.com.